right, AP Calc BC, Unit 3, Day 10, Parametrics. I think this is probably our last lesson. We're just going to apply what we've been talking about, two-dimensional motion, and bring some gravity into it for fun. So back when we did one-dimensional motion, rectilinear motion, we did some gravity problems, and vertical motion near the Earth's surface can be simplified as being affected by gravity only, but there, of course, are realistically other forces involved. But with that assumption, um, acceleration is due to gravity, which in English units is 32 feet per second squared. In metric system, it's negative 9.8 meters per second squared. It's negative because gravity acts downwards and pulls things down. This was the equation that we developed, and for position. But now we're going to be doing two dimensions. Now in two dimensions, the vertical motion is still affected by gravity in the same way. So we have the same exact equation, but it's just in the y direction, okay? In the x direction, horizontally, gravity does not affect it. It's just, it's going to gradually get pulled down. But, when you look at the path of an object being thrown at an angle, this motion, up-down motion, is affected by gravity. This motion is not, but eventually hits the ground and stops. Okay? So our horizontal acceleration in the horizontal direction is 0. And therefore, you don't get this extra term right here. So, velocity is the antiderivative integral of acceleration. So if that's 0, it's going to be 0 plus some c value, and then velocity just equals the initial velocity all the time. Okay, but then you integrate that to get position, and you get v naught t plus c, which is the initial position in the x. Now I use s here. I should probably just use y and x, but anyways. So let's do an example. A ball is thrown with a velocity, a ball is thrown at a 45-degree angle with a velocity of 64 root 2 feet per second from the top of an 80-foot building. What is the maximum height, time to impact, velocity, impact, length through a horizontal displacement, length of the ball's path? So a lot of the same questions that we've answered before. I would recommend drawing a picture showing the initial velocity at a 45-degree angle, 64 root 2 feet per second. Now what we're going to do is we want to break it down into the velocity. So that's the overall velocity. We want the velocity in the x direction, and that's the initial velocity. We want the initial velocity in the x direction, the initial velocity in the y direction. Now this is a 45, 45, 90, so we could just divide that by root 2, and we get 64. We could also use trig, basic trig, to get the different values. So I think it'd be good to write our equations first. So the equation in the y direction is going to be negative 16t squared plus the initial velocity in the y direction, t, plus the initial position in the y direction, which was 80 feet. This is y naught right here. This is v naught right here. Okay. And then velocity in the y direction is going to be negative 32t plus 64. And acceleration in the y direction is going to be negative 32, which should make sense because that's gravity. The x equation is going to not have this negative 16t squared because it has no acceleration. It's just going to have 64 initial velocity t plus the initial position in the x direction, which we're just going to consider 0. And then velocity is 64 all the time, and acceleration is 0 all the time in the x direction. So I think that's good to get that all figured out. So if we're looking for max height, then that means we need to use EVT. And we're looking for max y. So we need to take the derivative of y prime, which is also v sub y, and set it equal to 0. It is negative 32t plus 64. So t equals 2 is a critical point. We also call that a turning point in motion problems. We need the endpoints. Time 0 is usually an endpoint, and then the other time would be time of impact, which we're going to need for another calculations. Time to impact, the way we find that is we say, well, the height is 0 when it hits the ground. So that's going to be negative 16t squared plus 64t plus 80 equals 0. Factor in negative 16 out, t squared minus 4t minus 5. Keep factoring, t minus 5, t plus 1. And we get t equals 5 and t equals negative 1. Now, usually you get 2 times of time to impact from this gravity stuff because it's quadratic, so it has 2 solutions. We're not going to use the negative one. We're not going to go back in time. It's going to assume that we start at 80 feet, but it's going to assume, oh, we actually started at the ground before that. So now we have our endpoints are 0 to 5. So we're going to make a table and plug y in. We don't need x. 0, 2, 5. I'm going to plug them into the y equation. Now, when you plug 0 in, you get 80, which should not be a surprise. That's initial height. When you plug 5 in, you should get 0 because that's how we just found 5. When you plug 2 in, you get negative 64 plus 128 plus 80. So that's going to be 64. That's going to be 144 is your max height, which we probably could predict it would happen there, but this is the calculus back it up. So now we say the maximum height of the ball is 144 feet at time t equals 2 seconds by extreme value theorem. Checking endpoints and grid points. This is what I want on your upcoming test to get full credit for this kind of question. Justification, units. All right. Now we found time to impact. Time to impact is 5 seconds. And we want velocity at impact. Well, that's going to be a velocity vector, most likely. So we would say Vx at 5, which would be 64, and Vy at 5 would be negative 32 times 5 plus 64 is negative 160 plus 64 is negative 96, which makes sense. When you hit the ground, you're going downwards, right? So you should have negative y velocity. So the velocity at time of impact is 64 comma negative 96 feet per second are the units. Okay. We also want to know the length of the throw. Now, if I say I threw a ball, usually the length of the throw is like this, the horizontal displacement. I don't care how, if you hit a home run in baseball, they don't measure that necessarily. They say how far, how far it was to the fence or whatever, horizontal. So I'm trying to be clear here too. When I say length of throw, I mean how far did it go horizontally? And so that's just going to be the horizontal displacement, which is going to be the displacement in the x direction. And if we assume that, essentially what this is going to be, this is going to be x5 minus x0. And we're already assuming that this is 0 times 0. And so we plug 5 into our equation, 64 times 5, and we get 320 feet is the length of the throat. So then I want the length of the ball's path. So the actual length of the arc is what I'm asking for there. So that's going to need our new equation, which is the integral of speed, right? We've been using this from start time to end time, 0 to time of impact. It's going to be 0 to 5, square root of dx dt, or whatever, squared plus dy dt squared. I mean, you could write lots of different ways. You could write that. You could write x prime t squared. You could write v sub x t squared. Those all mean the same thing. Okay, so let's see what we get. So dx dt was 64 all the time, and dy dt was negative 32t plus 64 squared. I mean, we could see how far we could get by hand. You might say, oh, well, I could take, like, we could take a, no, what do we want to do? We could factor, what could we take out? We could take a 32 out of everything squared. I'm just trying to figure out how to make the number nicer. So 32 out squared would leave a 2 squared here, and then plus negative 1t plus 2 squared here, right? And then, so then you get 32 on the outside, and on the inside it'd be 4 plus t squared minus 4t plus 4 t squared minus 4t plus 8. Now, the only way we're going to be able to do this, I think, is if this is a perfect square, and I can't even factor that. So this is as good as I'm going to do, but we could have just done it on our calculator right at the beginning, or you could do it here. So I'm going to do 32. Actually, no, I'm going to act like I was just doing it from the beginning. Math 9, square root 64 squared plus parentheses negative 32 x plus 64 close squared close comma x comma 0 comma 5. Something's wrong. I don't know if I put no parentheses here. 64 squared plus negative 32 x plus 64 squared, close those parentheses, close parentheses there, x 0 5. I don't know what I typed in wrong. It looks good to me, but something's wrong. I don't know. I mean, I could do the other version, so that gives me an error. We could do 32 math 9 square root of x squared minus 4x plus 8 comma x, comma 0, comma 5. That one worked. So I don't know if I typed something in wrong. 396.448 feet. It's length throw. I don't know what I did. I could try it again. Math 9, square root, parentheses 64 squared, close, plus parentheses negative 32x plus 64 close parentheses squared, close parentheses and square root, comma x, comma 0, comma 5. Worked that time. So I guess I just typed something in wrong the first time. So there you go. So on the back, just have like a little summary of kind of everything that we've done. So anyways, for gravity at least. So we have parametric equations, dx dt or x prime. This is going to be the derivative of whatever the original x position function was. Acceleration is the second derivative with respect to time. It's not concavity. G double prime. This is going to be f prime of t, or dy dt, or y prime. Lots of different ways to write it. Second derivative of f. So lots of different ways. We're using this idea, this vector idea, where that's the overall velocity, and then this is going to be the horizontal and the vertical velocity components separately. And with gravity, this is just specific with gravity. Speed in general is the absolute value of velocity. That's the size of that. And the way we get that is by using Pythagorean theorem. Do Vx squared plus Vy squared. Or you could write it dx dt squared. I mean, there's different ways of writing velocity. And then distance has always been the integral of speed before, and it still is. So it's the integral of square root of Vx squared plus Vy squared. So if you know how to do speed, that should still work. Slope is dy dx, which is dy dt over dx dt. The second derivative, the concavity, is a little more complicated. And I showed you guys how we derived it. And you say, well, why is, it's going to be the derivative of dy dx again to get the second derivative with respect to x. But the problem is dy dx is in terms of t. So implicitly, we take the derivative of that with respect to the variable it has first, and then we follow it up by the derivative of that variable with respect to the variable we wanted the derivative of. And so then the equation ends up being dt dy dx over dx dt. I mean, you can try and memorize that, but if you can figure that, then it's hard to memorize. And I feel like if you guys can follow that idea of implicit differentiation, you can get it right every time. Flying horizontally, which is also where we consider maximum height, also endpoints, but it's when the slope of the tangent is 0, which is when this is 0 and this is hopefully not 0. It can be, but I have to use L'Hopital's rule. And I don't think I've shown you an example yet with that, so I'll probably at some point soon tell you. So hopefully that vertically, rightmost, leftmost, potentially, the slope is undefined because it's infinitely steep. Dx dt equals 0, and hopefully dy dt doesn't equal 0 at the same point. It can be, but things get harder. So that's it. A little summary of everything we've talked about in this chapter in one little less than half of a page. Your assignment is worksheet 310. Try it.